Hello. Today we are going to be doing a big Algebra 2 Precalculus review, and we're going to include essential subjects such as factoring, quadratics, graphs, imaginary numbers, complex numbers, rational functions, piecewise functions. We're going to be doing exponential functions, trigonometry, and some probability at the very end. So stay tuned for all of those. You can skip around in the video for specific topics. So first, let's suggest this. X minus 3 times x plus 4 equals 0. Now, how do you solve this? Well, if we have two quantities, essentially, if we have two quantities that multiply to 0, that means x minus 3 can equal 0. If x minus 3 equals 0, 0 times x plus 4 is 0, or x plus 4 equals 0. So, you just solve these equations. X is equal to negative 4, x is equal to 3. Those are your two solutions to this equation. Now, if we wanted to expand this, so x with the x squared, x with the 4 is equal to 4x. Negative 3 with the x is negative 3x. And then negative 3 with the 4 is negative 12. So then we combine like terms, x squared plus x minus 12. Those are the solutions here to this function here. Now, these are called zeros. Essentially, if we plot this on a graph, let's say the y-intercept's about here. Let's say this. Essentially what it's saying is that at this point, negative 4, and at this point, 3, there's intersections of the graph to the x-axis. So that's like finding zeros in a polynomial. Now, we're going to move on to a harder example that has a little more technical things, and it's going to involve complex numbers. So we're going to keep the graph there on the right. So essentially, what's going to happen is that we're going to have a sort of function here, 2x squared plus x plus 1 equals 0. So we don't have any factors to work with here, so we're just going to have to use the quadratic formula. Remember, x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. So let's plug it in. So x is going to equal negative b. B is 1. So we have negative 1 plus or minus square root b squared. Well, b is 1. So 1 squared is 1 minus 4 times a is 2. C is 1 over 2 times a. A is 2. 2 times 2 is 4. So if we simplify the inside of this radical, negative 1 plus or minus the square root, well, this here is just minus 8. So 1 minus 8 is negative 7. We put it over 4. But we see here that we have a negative inside, and this is not real. So in the set of real numbers, there is no solution for this equation. However, if we extend our understanding to the complex plane, we can essentially say that x is equal to -1 plus or minus I root 7 over 4. So those are going to be our two solutions, -1 plus I root 7 over 4 and -1 minus I root 7 over 4. Now, this I here, this is an imaginary unit. It's not a constant. It doesn't substitute for a value. It is a stable value. It is a stable thing that that essentially mathematicians discovered, where you can find solutions to problems that you would not be able to. For example, here, let's label this axis the imaginary axis and the real axis. This is called the complex plane, by the way. Essentially, these numbers, you think of a number line. Number lines are horizontal, right? This is 1, 2, 3, and 4. But in the imaginary part, imaginary is essentially a vertical number line that extends the real number system. So this is I, 2I, 3I, 4I. Now, when it says 4I, it's not referencing 4 times I, like exactly. I mean, it does represent that, but all it's saying is that it's 4 imaginary units. So this equation has no real solutions, but it does have imaginary solutions. And -1 plus or minus I root 7 over 4 is somewhere on the imaginary plane here, which means that our function here, let's say it's about, well, let's remove all of this, all of the real imaginary things. So if we actually plot this function, let's say it's here, and let's plug in 2 here. 2 times 2 plus 2 times 4 is 8. 8 plus 3 is 11. So plus 1, and then we put a 11 here. When we put 2 in here, give me a moment to erase that, because that is incorrect. Yep. So let's make this a little more accurate. So essentially, this is kind of what the graph looks like in some way. What essentially that means is that this function here has no intersection. So no intersection with the x-axis. Has no intersection with the x-axis, so that means it has no real solutions. So that's another way of graphing it and finding out how many solutions it has. Also, something that directly tells you how much the solutions a polynomial has is using the discriminant. Essentially, the discriminant is a section of the quadratic formula that tells you how many solutions it has. So for example, let's take negative, it's not, I mean, I guess technically, I'll just write this. B squared minus 4ac is a discriminant. Well, probably be more accurate to describe it using the Greek letter. The discriminant, that is a triangle. And essentially, if we have, let's say we have here 2x squared plus x plus 1. B squared, which is 1, minus 4 times 2 times 1. 1 minus 8, which is equal to negative 7. So, if the discriminant is greater than, or I guess equal to, probably 0 is probably a better benchmark to set, more specific. If it's greater than 0, then there are two solutions. If the discriminant is equal to 0, then there's one solution. And if the discriminant is less than 0, then there are no real solutions. So essentially, when we plug this into the quadratic formula, we saw that we had negative 7 inside of a square root. So we know that it's going to be it's not going to have any real solutions, which means it's going to have imaginary solutions, most likely. Not all functions and equations have solutions at all, in any world, complex or the real world. Now, let's move on to a different example. Let's say we have this figure. So, let's say that we have this figure. Now, we know that this side is x minus 3. Let's say that this side here is x squared minus 7x plus 13. Essentially, we're going to use some of the stuff that you learned in geometry to use your Algebra 2 skills to solve for x in this predicament. So, in geometry, we learned that, I understand that the drawing is not to scale, but we learned a theorem that tells us that these two chords are congruent to each other. Congruent means same in this case. So that means that x squared minus 7x plus 13 is equal to x minus 3. Now, when we see that x squared and this polynomial form, let's say give me a moment, ax squared plus bx plus c, what we want to do, and then let's say we have a quantity e, we want to move everything over to the other side, because then we have our thing equal to 0, and then we can use the certain properties that 0 holds to actually solve this equation. So what we're going to do is we're going to subtract x and add 3. X squared minus 8x plus 16 equals 0. See, now we're good to solve this one because we can factor this out. So this is how you factor. Essentially, 16, right, has factors, 4 and 4, 2 and 8. So essentially what we want to do is you want to try to multiply to 16 and add to 8. And we can use positives or negatives. So 2 and 8, can't really make 8 with that. 8 minus 2, 6. 8 plus 2 is 10. Not really any room there. But with 4 and 4, negative 4 and negative 4 are 16. But negative 4 plus negative 4, that's negative 8. So that's our factors here. So x minus 4 times x minus 4 is equal to 0. Now, we're going to express this in a different way. Two of the same quantities multiplied by each other is just a square. X minus 4 squared equals 0. Essentially, x is equal to 4, and only 4 in this case, because we only have one thing. So if we plot this on the graph, let's say this is 4, this means that our quantity here, let's draw a different one than that. Let's say this is 4. We have this. Their only intersection with the x-axis is at one singular point. So this means that means that the discriminant of this polynomial is 0, because it only has one real solution. It has 0 complex solutions. So that's how you apply your geometry skills and things you've learned in previous courses to essentially extenuate new algebraic processes like solving equations. So next we'll be going over a different topic here. We're going over imaginary numbers specifically. So let's say we have something, let's say we have I, and we raise it to some power. In this case, I doesn't technically have a value in terms of a number, so we can raise it to really high powers and still compute very small values. So I raised to the 205 is our end goal of what we want to solve. But first we have to understand what I is. I is essentially equal to the square root of -1. So that means that if we square both sides, I squared is going to equal -1. And let's multiply by I on both sides. I to the third is going to equal -I. And let's multiply by I on both sides. This means that I to the fourth is equal to, well, we have -I squared. I squared is -1 though, so -1 is equal to 1. So I to the fourth equals 1. So let's create a little table here for us to memorize. Let's have our i's on this side, and then let's have our numbers on this side. So I square root -1. Yeah, but I squared equals -1. I to the third equals -I. And I to the fourth is equal to 1. Obviously, you don't need to go past, because the process and the cycle just repeats after that, because when you multiply I to the fourth times I, it's just I again. So we're going to try to manipulate this exponent to making it into a form where we can simplify it down to one of these 4 options on what it could possibly be. So let's use some properties of exponents here that you've learned from Algebra 1. So for example, let's try to make multiples of 4 or multiples of 5 here with our equations. So 1 times anything is itself. So if we can cancel out multiples of 4, then that means we'll be able to crack down on the lowest solution. So essentially, 205, if we divide it by 4, that's about 51. So I to the 4 times 51 times, well, 4 times 51 is 204. Let's I to the first. So I to the 4 times anything. So I to the fourth is 1. 1 to the 51st is equal to 1. So now we have 1 times, we only have one I left over, so 1 times I is equal to I. I is the solution here. And I got my eraser finally working. Okay, now let's try another one. I to the 27th. So let's look for multiples of 4. So we have, well, we have I. 27 divided by 4. It's not quite 28, but it is 24. So I to the 24th times I to the third. 24, we can expand that out into 4 times 6 times I to the third. Well, I to the fourth is 1, so 1 to the sixth times I to the third is equal to negative I. So in this case, I to the 27th equals negative I. Now, let's do 2 more. Now, let's do I to 264th power. So, what we're going to do is we're going to try to take out these separate pieces. So I raised to the, well, 264 divided by 4, well, 4, well, I to the 4 times, well, 50, and then we're going to multiply, but we're just going to break this up because 264 is a big number. Well, 60 we have left is 4 times 15. And then we have those 4 I to the fourth here left over. Essentially, when we multiply these i's, everything's going to add. So 200 plus 60 plus 4 is equal to I to the 264. But since all of these are here, that means we have 1 to the 50th times 1 to the 15th times 1, which is equal to 1. So that's the answer there. Now, let's try a little more of a conceptual problem here. Let's say we have this expression, 1 over I. How are we going to find this out? Well, let's use the property that I is equal to square root of negative 1. So, 1 over the square root of negative 1. But we can't have, we can't have square roots in the bottom, so let's rationalize this denominator by putting it over itself. And essentially, square root of negative 1, any quantity over itself is 1. So, except for 0, obviously. So, when we multiply this out, we have the square root of negative 1, which is 1 times square root of negative 1, and the square root of negative 1 times square root of negative 1, when we have the square root of a times the square root of a, this is just equal to a. So, the square root of negative 1 times the square root of negative 1 is equal to negative 1. So now we have negative square root of negative 1. But the square root of negative 1, as we mentioned before, was I. So this means that negative I is equal to 1 over I. Very interesting, isn't it? It's so weird how the negatives end up popping up anywhere in math. So complex numbers are a very interesting subject, and they are used in many fields of study when it comes to this kind of thing. Now, in terms of complex numbers, let's say we have this function z is equal to 6 minus 2i. This is known as a complex number because it includes a real part and an imaginary part. Now, you're going to see some unfamiliar notation essentially regarding the real parts and the imaginary parts of this function. Let's use our graph real quick. Let's set it up so we can use it to interpret our answer. So, essentially, what they can ask you is to find Im of z. Or they can ask you to find Re of z. Essentially what this is saying is, it's not saying anything about z as a function. This Im and Re essentially mean is that what they want you to do here is they want you to find imaginary part of complex number. And this one wants you to find real part of complex number. So, let's analyze this function here. So, we have 6 minus 2i. So, let's find Re of z first. So Re of z, switch colors here, is equal to, well, this negative 2 is attached to the I, but this isn't. So the real part is just 6. That simple. Now, let's find Im of z. Now, the way we want to interpret this is, you want this to be a singular number. It does not include I in it because this is stating that number is the imaginary part. So in this case, we have negative 2 here. So Im of z is going to equal negative 2 and not negative 2i because it says that negative 2 is imaginary, is what it's saying. And we can't have double imaginary numbers, conceptually. So that's how you would find the imaginary and real parts of those. So that means when we plot this on a graph, let's say we have this graph. The way we plot 6 minus 2i is we take the real part of z is the x-axis, and the imaginary part is the y-axis, essentially. So 6 minus 2i, so if Re of z is equal to 6, that means we move our 6 on the x-axis, which is right here. Now, we know that Im of z is equal to negative 2. So that means we go down 2. So write 6, down 2. There we go. And let's make it a different color. There we go. So that there is that complex number 6 minus 2i. You're going to the right 6 and down 2 on the complex plane. Now, I want to stress something real quick. Multiplying by I, essentially what this is going to do, it's going to be way more obvious when we look at the graph. But let's say we had to expand something like 3 plus 2i times 4 minus 3i. When we multiply this out, 12, negative 9i, positive 8i, and then negative 6i squared, what we're doing essentially is we're creating this thing, I squared is equal to negative 1 plus 6 minus I, and then we're essentially creating 18 minus I. So essentially, these two factors have no higher degree than the other ones because they have a special property when we look at them in the plane. So let's say we wanted to actually multiply this point right here, this function, by I. So we'd say we have I times 6 minus 2I. What we're going to do is we're going to use our normal algebra distributive properties. Let's move those in. So 6I minus 2I squared. 6I, and then, well, I squared is -1, and -2 times -1 is +2. So let's obviously switch this order around. The z is equal to 2 plus 6I. Well, let's use a different color. So 2 is the real part, so we move over 2. So as we move over 2, then, well, the imaginary part is +6, so up 1, 2, 3, 4, 5, 6. So it's going to be about at that point, right there. Obviously, we're going to graph it. And let's use green. So essentially, what's happening is when we multiply by I, what we're going to be doing is we're going to be creating a sort of circle around. So if we have a graph of 1, let's say this is 1, -1, I, -I. Every time we multiply, so that's why I squared equals -1. Essentially, what's happening is when we multiply it by I, it moves right here, moves here, and moves there. So it creates a whole circle around the complex plane. Essentially, I is meant to rotate complex numbers, rotate points in the complex plane. So conceptually, that's how the imaginary numbers work. Now, let's get into some other topics. So, let's go over rational equations. So 3 over x minus 1 is equal to x plus 2 over 6. So let's cross multiply. Essentially, what we're going to get is we're going to get 18, which is 3 times 6, is equal to x plus 2 times x minus 1. Y'all know how to FOIL this. X squared minus x plus 2x minus 2. And then we just combine these like terms. X squared plus x minus 2. There we go. Is equal to x squared plus x minus 2. And let's just erase this because we solved this already. So what we're going to do, remember, is we're going to bring this to the other side because we need to set this equal to 0 because we need to solve it because it's a quadratic. So we have x squared is equal to x squared. Oops, that is my bad. X squared plus x. Well, -2 minus 18 is -20. Well, let's set this equal to 0. So here, we can just factor this out. -20 has some factors. 10 and 2. 4 and 5. So, essentially, are we going to be able to make 1 our b? Essentially, we have to find two numbers that multiply to -20 and then add to 1. So in this case, 10 and 2, we can only get 12 and 10, depending on how we subtract and subtract and add. So it's not going to be this one. It's going to be these. Now, which one do we make negative? Because we need at least one negative number, because a negative number times positive number is negative. So one of these has to be negative, but we have to make, but b is 1. So that means that this number has to be negative because 5 minus 4 is 1. So now we just take these, x minus 4 times x plus 5 is now equal to 0. So now we solve. Now we know that one of these has to be 0. So x equals 4 and x equals negative 5. Now you do have to be careful if there's any extraneous solutions, because you see in this denominator right here, if we had a polynomial that has a solution of 1 here, x could not equal 1 because 3 over 0 is undefined. But in this case, we don't have that. So x is equal to 4 and negative 5. So next, we're going to be talking about the graphs of these rational functions. So essentially, what's going to be going on is we're going to have asymptotes. Asymptotes are essentially how a rational function approaches infinity and its domain, its range, all the above. So we have 3 over x plus 1. Let's say we have f of x equals this. So f of x is y, by the way. So essentially where a over bx plus c, the horizontal asymptote, or let's use HA, is at y equals 0. But at, let's say, ax plus b over cx plus d, the horizontal asymptote is equal to a over c. So essentially, when it was only first degree, the horizontal asymptote is always y equals 0. But if the degree is 1, well, in this case it'd be x is 0, which is just 1. But in this case, a to the x plus b, essentially, if it's a first degree polynomial, then these coefficients of these x's is going to be your horizontal asymptote. So let's practice. So essentially, what we're going to do is we're going to find the horizontal asymptote. In this case, we only have a 3 on the top. There's no x coefficient on top. So that means it's going to be at y equals 0. So this is going to be the horizontal asymptote here at y equals 0. Now, essentially what we're going to do is we're going to find the vertical asymptote. The vertical asymptote is essentially what makes the bottom part equal to 0. So in this case, it is equal to the undefined part of the rational function. So essentially, if we say that x plus 1 equals 0, that means 3 over 0, it's undefined. So that's going to be the asymptote, because this function is actually, as it approaches, like whatever x plus 1 equals 0, so obviously we could solve x equals negative 1. As x is approaching negative 1, it's going to be heading towards infinity. It's going to be heading towards infinity because 3 over 0 is undefined. So it's going to be diverging off. It's going to be approaching, but it's never actually going to touch that line. So if we set up a little asymptote here, let's say this is negative 1. We're going to use dotted lines, and then we know that we have a horizontal asymptote here, and essentially we could just plot some common points to see exactly where this function is going to or what this function is going to behave like. So let's use 1 for example. When x equals 1, y equals 3 halves. So this is 1, and 3 halves I would say is about right there. Let's use 2. If we use 2, y equals 1. So if x equals 2, y equals 1. So we could gather a rough sketch. So obviously note that it will never touch any of those. And then obviously it's going to be symmetrical on the other side. So we'll just use this right here. That's just a rough sketch of how it's going to look. And those are the asymptotes for that specific one. And that's how you graph it, is you use those asymptotes. You can find some common points, find the critical points. You can use all of those to find the graphs of these rational functions because they have certain domains and all of that. Let's have another example. So let's say f of x is equal to, let's say 3x minus 2 over x minus 4. So here we have ax plus b over cx plus d form. Essentially this means that 3, which is a, over 1 is equal to the horizontal asymptote. So the horizontal asymptote is equal to 3. So at y equals 3, let's say that's about right here. We have a horizontal asymptote. And then let's use black for our vertical asymptote. So what is going to make this bottom part 0? Well, let's set x minus 4 equals 0. X is equal to 4. So at x equals 4, let's say that's right here. That's going to be where the function is trying to approach, but it's never going to touch. So what this means here is that when we graph our function, let's use, well, is it going to be approaching 3 in which direction? So essentially what's going to happen is that we have our horizontal asymptote is at 3, but at which direction are we going to be approaching it? Well, in this case, we're likely going to be approaching it from, well, we're going to have a function here, right? Because obviously it has these asymptotes here. It's going to fit in with all of that. And then we're obviously going to have this section that obviously never crosses. Here, I'll probably redo that. Yeah. So we essentially have this kind of graph where it's never going to touch y equals 3. It's never going to touch x equals 4 on the graph. These are the asymptotes. So that's how you find asymptotes on rational graphs. Now, let's work more with rational numbers. So what we're going to do is, let's say we have this situation. Let's not use this color. The cube root of 2x plus 1 is equal to 3. So let's use some basic algebra to, let's cube this entire thing. Essentially, the cube and the cube root are going to cancel, and we're going to be left with 2x plus 1 is equal to 3 cubed. Well, 3 cubed is equal to 3 times 3 times 3, which is equal to 9 times 3, which is equal to 27. So 2x plus 1 equals 27. Now, we subtract 1. 2x is equal to 26. So that means x is equal to 13. So that's the solution to this equation. Now let's plug in to see if there's any extraneous solutions here. So 2 times 13 plus 1, which is 26 plus 1, which is equal to square root of 27, which is in fact 3. So we did verify that, yes, this is an actual solution, because you can find some extraneous solutions in these. Let's go on to another example here. So let's say we have some sort of equation. Let's say the square root, that is not the right symbol to use. The square root of x minus 7 is equal to negative 4. So let's just solve it. So to get rid of the square root, we square everything. So that means x minus 7 is equal to negative 4 squared, well, is 16. Let's subtract, or in this case add, sorry. X is equal to 23. Let's check for extraneous solutions here. So let's plug it back in. So we have the square root of 23 minus 7 is equal to negative 4. So now we have the square root of 16 is equal to negative 4. But wait, this is wrong because the square roots can't produce negative values. So this means that this has no solution. In fact, it has no solution in the set of real numbers and in the set of complex numbers. So this equation has no solution at all, no matter what numbers we use. Let's move on. So let's say we have a function x minus 1 times x plus 3 times x minus 4. Let's plot it. I'll just use this f of x. So let's use up the zeros. So the zeros are 1, negative 3, and 4. So let's point them out here. 1, 4, negative 3. So essentially, we're going to find out, is the function increasing or decreasing over these x values? So let's plug in some values between, well, let's say a value less than 3. Let's say negative 4. So we have negative 4 minus 1, which is negative 5. Negative 4 plus 3, negative 1. And negative 4 minus 4 is negative 8. So all of this is just 5. 5 times negative 8 is negative 40. So this number is negative. So let's create a little chart here. So this means that negative 3, let's have 1 in the middle, and then 4. That means over here below negative 3, the function is decreasing. Now let's find a number between negative 3 and 1 that we could plug in here, and let's see how it shares. So let's plug in 0. Probably an easy number. Negative 1 times 0 plus 3 is 3. 0 minus 4 is times negative 4. This is just equal to 12. So this means that over this, it's increasing. Now, let's choose different y values. So any number between 1 and 4. Let's choose 2. So 2 minus 1 is 2. Oops. 2. That is wrong. Give me a moment. So 2 minus 1 times 1. All right, so this is the expansion here. Sorry about that. So this is the expansion. 2 minus 1 is 1. 2 plus 3 is actually 5. So 5 times negative 2 is negative 10. So that means that now the function between here is decreasing. Now let's pick a number bigger than 4. Let's say, we'll do 5. So 5 minus 1 is 4. X plus 3, 5 plus 3 is 8. 5 minus 4 is 1. So this is 32. 32 is a positive number, so it's positive. So it's increasing past this. So what this means here is that below here, it's decreasing. So the function is decreasing here onto this. But now, but the thing is that the function is going to increase onto this and then decrease onto this. And then when it goes past this, it's going to go back up eventually. This is obviously a very, very rough sketch here. Let's highlight these zeros. So this is how you're going to plot this function, is essentially find those intervals of decreasing and increasing, and then you can use them to plot the function and see how the graph is going to behave. Let's tackle a couple more topics, and I hope this video won't be too long, but it's in characteristic, it's going to be a long video. So let's say that we have this, negative 2 x squared plus 8x minus 2 equals 0. We're going to put this in something called vertex form to try to make us find vertex. Our vertex form is essentially a times x minus h squared plus k. So what this means, where their vertex is h comma k. So essentially, if we have, let's say, x minus 1 squared plus 1, that means our vertex would be at 1 comma 1. So let's use some properties and some quadratics and algebra to switch this around into this form. So for example, let's move the 2 to the other side because we want to complete the square most of the time here. Negative 2x squared plus 8x. And let's leave a little slot here, and let's put 2. Let's factor this out. Negative 2 times x squared minus 4x, and then we're going to leave a little space, is equal to 2. It's the same thing still. Now, what we're going to do, well, there's multiple things we could do, yes, but in this case, we could divide by 2. Let's take x squared minus 4x, and then, well, negative 2 divided by negative 2, which is equal to negative 1. If we add 4 on both sides, essentially, we're taking b over 2 squared. That's how we're going to find our perfect squares, b over 2 squared. And negative 4 over 2 is negative 2. Negative 2 squared is 4. So what this is going to do is this is going to create a perfect square, which is going to help us put it in this form. So now we have this x minus 4 squared. This here is negative 1 plus 4, which is equal to 3. So x minus 4 squared plus minus 3 that's going to be our function here. So we have a vertex at h, comma k. H, well, it's x minus h, and we have a minus 4. Minus 4 is a 4. Minus 3, well, k is positive, so that means that our y is negative because we have negative 3. So we're going to have a vertex there in that function right there. Now, there is another way to do this, and I think it's actually the better way, because when we did that, we did not take into account a factor of the quadratic. So, essentially, what we're really supposed to do is when we add 4, really, what we're saying is we're adding negative 2 times 4, which is negative 8. So in this case, we're subtracting 8. Let's subtract 8 on both sides. So now we have negative 2x minus 4 squared minus, well, in this case, plus 6 is f of x. Because this is negative 6, and we're going to move it to the other side, it's going to be positive 6. So really, this vertex is 4, 6. The reason for it is because now we have this form right here. We didn't divide this out. Do not divide it out. So let's say we have here 4, and then 6, I would say, is about right here. So that means the vertex, well, in this case, let's notice that we have negative 2x squared. This means it's going to be a concave down graph. So that means that this vertex is a maximum. Essentially, it's the highest that the graph is going to go. So, next thing up is inverse functions. Inverse functions are essentially functions that are essentially inverted over y equals x. So, if we have the function f of x is equal to x squared minus 2x plus 1, let's say we want to find inverse function f of negative 1x. What we're going to do is, let's say if we have y is equal to ax plus b, that means y inverse is going to be x equals ay plus b. So essentially, what's going to happen is that we're going to just substitute x for y, and we're going to interchange them, and then resolve it back. So let's let f of x equal y, just for simplicity's sake. So y equals x squared minus 2x plus 1. So let's change y out for x. So let's realize something. Let's factor this out. So we have 1. 1 only has 1 and 1. But we can make them both negative, because two negative numbers multiply to a positive number, and those add to negative 2. So we have a perfect square on our hands. Specifically, x is equal to y minus 1 squared. So let's just solve this like a normal equation. We're going to take the square root. We have the square root of x is going to equal y minus 1. Now all we got to do is add 1 on both sides. Y is equal to the square root of x plus 1. Essentially, it's just going to be our square root function. And the y-intercept at 1. In that case, it's going to be our inverse function. But if we take our other function, let's graph it here. It's going to be reflected over, let's use this as an approximation. So it's going to be reflected over line y equal x. So that's essentially how inverse functions work. You're substituting y in for x and then resolving for y for the equation in terms of f of x. All right. So piecewise functions. Essentially, let's say we have a function f of x is equal to, we're going to use a series of terms here, 3x minus 1, whereas x is greater than 1. So we have 2x squared, whereas x is less than 1. And let's say we have 3 to the x if x equals 1. So essentially, let's find f of 6, f of negative 1, and f of 1. So f of 6, essentially, you're not going to just want this to plug this into all of them. You will only want to plug them if they're in a certain domain. So x equals 6 only falls in the domain of this one here. So that means that we're going to have f of x is equal to 3x minus 1. Now f of 6 is going to equal 3 times 6 minus 1. 18 minus 1 is equal to 17. So it means f of 6 equals 17. Now let's compute f of negative 1. Negative 1 is only in the domain of this 2x squared. So essentially, we're going to have 2 times negative 1 squared, which is going to equal 2 times 1, which equals 2. So f of negative 1 is 2. Now, f of 1, well, f is not defined because it's not greater than 1, no less than 1, but when it's equal to 1, we use this function, 3 raised to the x power. So 3 raised to the x power, which in this case is 1. So that's equal to 3. So f of 1 is 3. Essentially, you're plugging in your answers into the domains that they belong into, and then you plug them in, and then you chug them in. So that's how piecewise functions work. They can be graphed, but that is a discussion for another day, because it has to deal with various topics that are long and not interesting. So let's say we have this equation. We're not going to call it a function exactly. X plus 1 squared plus y minus 1 squared is equal to 16. Is this a function? Well, it is not a function because it's not in terms of y is a function of x. It's x squared, it's x and a quantity squared plus y quantity squared is equal to a whole nother value. So this is not a function. This is more of an equation. So essentially what this is going to be, this is the circle equation. So we have x minus h squared plus y minus k squared is going to equal r squared, whereas r is going to equal the radius, and h comma k is going to equal this, is going to be the center. So in this case here, let me rewrite this. X minus h squared times x minus k squared no, in this case, y minus k squared is equal to r squared. So our r squared is equal to 16 in this case. So that means r is equal to 4. So our radius is going to be 4. But our circle is not going to be centered around the origin in this case because we do have some components. Because if it's centered around the origin, it would be x squared plus y squared, and there would be no other components. So our center is hk, but h and k are both negative. So if the value is negative, then it's positive. But if it's positive, then it's negative. So this value here, essentially, x minus h and minus negative 1. So that means h is equal to negative 1. So this is negative 1 is our x value. And in this case, y is going to equal 1 because we have negative. So y minus k, that means k equals 1. So that's going to be our center. Now, let's move it over. This is going to be it. And our radius is going to be 4. It's going to have a length of 4 units. So that means, let's plot it. For example, let's go up 1, 2, 3, 4, 5 units. And then, all we got to do is build a circle. Let's immediately delete that. All we got to do is build our circle now. Obviously, it's a rough sketch because building circles is very difficult. But we have a center of a circle, and all of its portions are equidistant from the center because our center is a circle. So its center is the same distance away from all the edges of the circle. So that's the equation for a circle. It is not a function because it does not pass the vertical line test. Essentially, drawing a line that is vertical on a graph, if it inflects at 2 different points, then it's not a function. But here's another thing. So let's say let's calculate these. Sine of pi over 2, cosine of pi over 3, tangent of 5 pi over 6, and cotangent of 3 pi over 4. So in radians, we're going to have to try to find these values. Now we're going to use a unit circle. I'm not going to exactly memorize the unit circle, but I expect that you have an exam sheet or something you can use to memorize this unit circle. So in this case, on the unit circle, it has a radius of 1. Obviously, this case is not centered because I'm bad at this. Essentially, what's going to be going on is that these points to the center are going to be cosine theta, which is some angle, sine theta. It's essentially this is x and this is y. So in this case, we're going to convert to degrees, and let's see if it's directly on that unit circle. So pi over 2, to convert it to degrees, we're going to multiply by 180 over pi. These pi's cancel, and 180 over 2 is equal to 90. 90 degrees is right here, which is 0, 1. And as you can see, sine of theta, which is the y value, is 1. So that means sine pi over 2 is 1. All right. Next, what we're going to do, cosine of pi over 3. Pi over 3 times 180 over pi, which is equal to 180 over 3, which is equal to 60. 60 is on the unit circle, in fact. And and it intersects at a certain point. In this case, if you look at your reference sheet here, you can see where it intersects. Now, the thing with the unit circle is that it intersects at some irrational numbers, like square root of 3 over 2, and all of the other things, 1/2, square root of 3 over 3. So you're going to have to find a way to memorize this, and there is some pretty good ways to memorize this because it does have some sort of pattern. It does have some sort of pattern to follow, but in this case, it's 60. So the coordinate here is 1/2, comma, square root of 3 over 2. And sine theta, or sorry, cosine theta is the x value. So this one is equal to 1 over 2. All right. Now, let's use some trig identities here. Solve this one. Tangent, well, we have cosine and sine, so how are we going to find tangent? We're going to use this property here that tangent of theta is equal to sine theta over cosine of theta. So we're going to be dividing our x and y values. So we have tangent of 5 pi over 6. So 5 pi over 6 times 180 over pi. So let's get rid of the pi's, and let's put 30 on the top. This is going to be equal to 150. 150 is actually, in fact, on the unit circle. Let's make it this point here. This is negative root 3 over 2, comma 1/2. So, essentially, tangent theta is going to equal sine theta over cosine theta. Well, sine is the y, so we're going to have 1/2 divided by the negative square root of 3 over 2. So when we divide, let's multiply by the reciprocal. So we have 1/2 times, let's just put negative on the outside. Negative, well, when we divide by square root of 3 over 2, we're really multiplying by 2 over square root of 3. Now, the 2's cancel. We're left with 1 over square root of 3, which is equal to the square root of 3 over 3. And obviously, we're going to put the negative on there. And that's going to be our answer there. Negative square root of 3 over 3 is equal to tangent theta. Now, let's find cotangent. Cotangent is equal to, oops, that is technically not the right notation. Cotangent theta is equal to 1 over tangent of theta. The tangent of theta is equal to sine of theta over cosine of theta. So that means cotangent of theta is going to equal cosine of theta over sine of theta. So let's convert it to degrees. So 3 pi over 4 times 180 over pi. The pi's are going to cancel. 180 divided by 4 is 36. No, I'm just kidding. It's 45. 45. 45 times 3 is 135, which is actually, in fact, on the unit circle. It's at this point right here, which it's at point, let me think, negative square root of 2 over 2, comma, negative square root of 2 over 2. So this means that cotangent of theta is going to equal negative square root of 2 over 2 over negative square root of 2 over 2. So these negatives are going to cancel. So the square root of 2 over 2 times 2 over square root of 2, we're going to have everything cancel out, and this is just going to be 1. So this means that this is equal to 1. So that's how you use the unit circle to find values of trigonometric functions here. And each one has a specific value, and there's so many good properties about the unit circle that are very applicable to studies of trigonometry and geometry as such. Now, let's dive into logarithms and exponentials. Essentially, what's going to happen is that we're going to have something called a logarithm. A log, let's not use this visceral color. Let's have black. Log base A of B is going to equal C. Now, essentially what this is trying to say is that A raised to the C is equal to B. But this is like essentially the inverse of saying this. So if we have some sort of thing, log, let's say base 3 of 9, what does that equal? So essentially it's saying 3 raised to some quantity, let's call it x, is going to equal 9. In this case, we can just guess what it is. In this case, it's 2. So x equals 2. So that means this is equal to 2. But another way we can actually verify that this is equal, if we have 3 to the x is equal to 9, there's certain properties of logarithms. So log of x times y is going to equal to log x plus log y. Log of x over y is going to equal log of x minus log of y. And log of x raised to the y is going to equal y log of x. So in this case, we're going to use this here. We're going to take log base 3 on both sides. So what we're going to do is we're going to have x log base 3 of 3 is going to equal log base 3 of 9. Log base 3 of 3, this is just 1 because 3 raised to the 1 power is 3. So x is going to equal log 3 of 9. Log 3 of 9 we've already discussed is 2. So this is the way to solve it if you don't actually know, if it's not perfect or it's not the same, it's not like a very common sort of answer that you can compute in your head. Now, let's use some quick equations and some different types of logarithms here, and let's find out some more about them. Let's say we have log base 2 of 1/2. What is this equal to? Well, this means that 2 to the x is going to equal 1/2. So 2 raised to what power? So this number is smaller than 2, which means we're gonna have a negative thing because this is a reciprocal of 2. The reciprocal is -1. So that means x is going to equal -1 here in this case. So that means that log base 2 of 1/2 is -1. The outputs can be negative, but the inputs, you can't, this number right here cannot be negative because any number raised to a rational or irrational number has to be positive. So it only works in the complex world. So essentially, let's use that information for our next example. So essentially, we're going to have this thing called a natural logarithm. Essentially, we're going to use this e. E is equal to 2.718, and then it goes on forever. It's sort of like pi in that sense. But this appears in a very different branch of mathematics, where let's say we have compound interest rate. 1 plus 1 over x raised to the x. Let's say that this is the compound interest formula. Let's say that this here, this is compounded an infinite amount of times. So 1 plus 1 over infinity raised to the infinity. This is e. So that means that if you were to infinitely compound, if you were to put $1 in the bank and then infinitely come back to compound your interest, that means the max amount of money that you could ever get is $2.71, essentially. So e appears everywhere in mathematics. In this case, we have natural log. Natural log is essentially just a shortcut way of saying log base e. So ln of e is equal to 1. Ln of 1, well, e raised to the x power is equal to 1. If we take natural log on both sides, x is equal to ln of 1. But in this case, any number, x raised to the 0th power is always equal to 1. So we can use our judgment here and say that ln of 1 equals 0. Now, what about ln of 0? Well, ln of 0 is actually undefined because when we have a number raised to a number that is unzero, obviously, we don't have any solution to this equation at all. So this means that this is undefined in the real world. Most of the time in the real world and complex world, but sometimes only in the real world. Now, let's say we have an exponential equation, 2 raised to the x equals 32. Let's say we don't know the answer immediately. How can we find it? Well, we'll take log base 2 on both sides. This x log base 2 of 2 is 1 is equal to log base 2 of 32. Log base 2 of 32, 2 raised to what power is 32? It's 5. So x equals 5. Oops. So that's how you solve exponential equations. Now, logarithmic equations are a little bit different because they deal with logs. Logs are less pretty looking, I would assume. So log 3 of x, of some value x, is equal to 4. The process to solve this is that what we're going to do is we're going to take this 3, and what we're going to do is we're going to move it and place it under this 4. So 3 raised to the 4th power. So log, actually, to be more specific, we're canceling out all of this. So essentially what we're saying is that x is going to equal 81 because 3 to the 4th is 81. Now, let's use some geometry here. Let's say we have, let's use a line. let's say we have an angle. I'll use blue. Let's say we have some interior angles. Let's say one of them is 6 raised to the x. The other one is 144. Find x. So to find x, we're going to have to use the fact that, or actually, let's assume here that these are some parallel lines. So, what we learned from geometry, that those are going to add up to 180. They're supplementary because they're same side interior. So 6 raised to the x plus 144 is going to equal 180. So let's subtract. 6 raised to the x is going to equal to 36. Now we're going to have x is going to equal log base 6 of 36, which x equals 2. So in this case, if you wanted to find this, that means that this angle would be 36 degrees. So that's how you solve exponentials. Now, let's dive into our last two topics. So, we have, I don't know how I'm going to remove these from the screen, but all right. Anyways, we'll just keep them on the screen. We might as well. Let's divide our paper. So, essentially, we're gonna have some functions. So let's take some functions. F of x is equal to, let's say, x squared. And we have g of x, just another name for a function, is equal to x to the third minus 8x. And then we're going to have x to the fourth plus 3x. Well, let's set that equal to h of x. So we're going to discover the concept of odd, even, and neither functions. So I understand that I spelled neither wrong. So an odd function essentially means that f of negative x is equal to negative f of x. That's an odd function. Now, an even function says that f of negative x is equal to f of x. So, directly means that. Now, neither, what this means is that f of negative x is not equal to negative f of x. That's what that means. Obviously, if f of negative x was negative, that means we only use the test if it's the odd criteria. We don't use the even criteria when trying to decide if it's neither, because odd and neither are the ones that correlate, and then even is if it's neither of them. So let's practice with these functions here. So essentially x squared. So let's have some easy number. Let's say 2. So f, let's use, for example, let's not use that color. Let's use 2. So f of x equals 2, or probably more accurate, f of 2 equals 4. Sorry. But f of negative 2 also equals 4. Now, that's the even criteria. What about the odd criteria? The odd criteria says that f of x, so f of 2, is equal to 4, meaning that negative f of 2 should equal 4, but it doesn't. It equals negative 4. So it's not odd. And if it's neither, that means that f of negative x Yeah, so that means f of negative x, so f of negative 2, is not equal to negative f of 2. So f of negative 2 is 4, or it's not equal to negative 4. So it's not this. Essentially, what happens is that this is an even function. So that means this here is even. Now let's check this one. X to the third minus 8x. So when we have x to the third minus 8x, essentially what's going to happen is we're going to have to plug in some value, x to the third minus 8x, and we're going to determine whether it's odd, even, or neither. So x to the third minus 8x, let's plug in some easy value. Let's say 1. So 1 minus 8 equals negative 7. So essentially, f of 1 is equal to negative 7. Let's find f of negative 1. F of negative 1, well, negative 1 to the third is negative 1 minus negative 8 times negative 1 is plus 8. So this is equal to 7. So f of negative 1 equals 7. What about negative f of 1? Well, f of 1 is 7. Negative 7 is just 7. So let's get rid of all the scratch work. I'll rewrite this function here. So this means that, well, we can say that f of negative 1 is equal to negative f of 1. So that means this right here is an odd function. Now we can say, we can look at this function here and say that is an odd function. Now, h of x to the fourth plus 3x, let's analyze this function. So let's plug in some value, 1. Let's find our, so let's find our f of 1, so our f of 1, 1 to the fourth plus 3 is 4. F of negative 1, well, negative 1 to the fourth is 1, but negative 1 times 3 is negative 3, so it's 1 minus 3, which is equal to 2. And negative f of 1 is just equal to negative 4, because f of 1 equals 4. So this means, so there's no same values here. So when you see none of those same values, that means that this is neither even or odd. It's neither even or odd. So that's how you classify functions on whether they're even or odd. Now, there's going to be one last concept that is a little more abstract, but you'll find it in the Algebra 2 courses and Precalc courses, especially in the honors system and variety. So, we're going to introduce a certain concept called permutation and combination. So, essentially what this is meaning is that we have some sort of thing. These graphics are very, very annoying. Don't know if I can undo back. There we go. So essentially what we're going to be doing is that we're going to have some combination, we're going to have some subset, and what we're going to do is we're going to choose a certain amount from that subset, and then we're going to see how many of them we can do. So we have, let's say we're going to use this notation, by the way. We're going to use n, probably not the best color to use. So let's have p. This is a permutation, this means. We're going to have n, and we're going to have r. Essentially, what this means is that n is the number of objects. This is the objects, and this is the selected. This is the selected. So, in this case, order does actually matter in terms of this. So if we had, let's say, 4 objects, or in this case, actually, 6 objects, pick 4. So we're going to be talking about permutation because this is P. So this, we're going to follow an actually very complicated formula where we have n factorial over n minus r, and we'll assign a color to these factorials. N minus r factorial. So essentially, we're going to plug these values in. N equals 6, so 6 factorial over 6 minus 4, which is 2 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Essentially, it's how many times can you arrange 6 objects. And then we have 2 times 1. So the 2's, 1's, and these are going to cancel out. So now we're left with 6 times 5 times 4 times 3. So here, this is 30, this is 12, and 12 times 30 is equal to 360. So in this case, there are 360 permutations of 6 pick 4. So let's dive into another thing, combinations. So what we're going to have for combinations is we're still going to have a similar thing. We're still going to have a similar thing, but it's going to be a little bit different. So we're going to have n, c, r, where n is our objects, or number of items in the set, and number of items selected is still going to be r. However, our formula is going to be a little different because the order does actually matter. So we're going to have this. We're going to have n. Here, I'll just list out the formula. Oh, oops. There we go. There we go. So we're gonna go by this formula here. So, well, let's give an example. So let's say we have 5 objects. Oops, 5 objects. And let's choose 3 of them out of the set. How many combinations are we gonna get? So n is 5. So 5 factorial over n minus r. Well, 5 minus 3 is 2. So 2 factorial times r factorial. R is 3 times 3 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. 3, 2, 1, and 3, 2, 1 are going to cancel, and we're going to be left with these 4s and 2s canceling out. This is going to be 2. So this is going to equal 10. There are 10 possible combinations of 5, choose 3. So that is how probability works, and essentially that is essentially the most of Algebra 2. It's about exponentials, it's about functions, relationships, probability, trigonometry, plotting functions, inverse functions, applying geometry, using complex numbers to solve unsolvable equations, piecewise functions, and essentially the classification of graphs, along with evens, odd functions, y-intercepts, x-intercepts, vertexes, and all of the above. So I hope you like this video. It's obviously a very long video, but this video has taken forever to make, so I do appreciate all the people who watch it. So if you need more review, I'll have more on my channel soon, and I will see you guys later. Goodbye.